We may have to rewrite all the textbooks on the beginning of the universe, says Michio Kaku. It takes many billions of years to create a galaxy like the Milky Way, with its 100 billion stars. However, the James Webb Space Telescope has identified 6 galaxies that existed just 500 million years after the Big Bang, and they are up to 10 times larger than the Milky Way. There's no turning back now. The telescope has discovered one of the oldest galaxies of all time, so huge and luminous that it cannot possibly be a galaxy from the early universe. Kaku suggests that we are at the beginning of a new era in physics, potentially giving more room to models like string theory and the multiverse, which could finally solve the Hubble tension. He humorously remarks on the discoveries of the James Webb Space Telescope, which has shown us galaxies in the early universe that are so large and evolved that they must have formed before the Big Bang. There has been evidence suggesting that our understanding of the universe does not completely match reality. Known since the 1990s, the Hubble bias is a measurement inaccuracy in determining the universe's expansion rate, but no one has solved the puzzle. Now, Webb shows us that there are deeper issues with our cosmology and astrophysics. If galaxies were already on the move 250 million years after the Big Bang, as Kaku points out, the Big Bang could not have taken place 13.8 billion years ago. According to our current understanding, galaxy evolution is a complex process that takes billions of years to produce galaxies like the Milky Way. Webb has discovered dozens of ancient, beautifully shaped, large galaxies that challenge our understanding. Moreover, Webb has shown us images of very large black holes containing more than 1 billion solar masses just 500 million years after the supposed Big Bang. These findings indicate that our scientific understanding was incorrect, and the launch of the James Webb Space Telescope has triggered one of the biggest crises in modern cosmology. Some of the newly discovered galaxies appear up to 10 times larger than the Milky Way, as Kaku points out, laughing. The popular astrophysicist from the USA has long highlighted the gaps in our science. His theories, which aim to unify quantum field theories with the astrophysics of large phenomena, were not taken seriously by conservative scientific circles. Now, these conservative camps face a huge problem, as their rigid views on the cosmos, matter evolution, and the Big Bang are tottering. Instead, we will gain new physics, and thanks to Webb, we may discover completely new aspects of our universe. They cannot claim ignorance because, in addition to the Hubble telescope, there were already indications before Webb that the old idea of the Big Bang and expansion was not entirely correct. Even the old Hubble Space Telescope discovered suspicious points of light in the early universe. One such discovery was the galaxy known as GZ9P3, initially recognized as a vague spot of light but later revealed by Webb to be a very old galaxy. Webb's sharp eyes showed a redshift of 9.3, meaning we are looking at a galaxy that existed only 510 million years after the Big Bang. This galaxy, far more massive and mature than expected for its age, also has a strange shape with 2 bright spots, suggesting a galaxy merger. Such mergers in the early universe would not be unusual, but even separately, these galaxies are too large and evolved to be baby galaxies. Our old standards suggest it takes billions of years for galaxies to mature, yet we see this galaxy as it was 510 million years after the Big Bang. The galaxy is dominated by young, bright stars, and researchers found elements like silicon, carbon, and iron, indicating older stars. These elements are not typical of the first stars, speaking against this being a young galaxy. Thus, something is not right, and scientists have not yet found the solution. The discovery of more old stars suggests that stars formed earlier and enriched the universe with metals faster. The old stars in GZ9P3 may show that the galaxy matured chemically faster than thought, or we may have been wrong about the universe's age. This brings us back to the Hubble tension: is expansion a lie? Did you know that the expansion of the universe has never been fully proven? The idea that the universe is expanding is a theory with significant evidence, but problems with this theory soon emerged. Expansion is a cornerstone of modern cosmology, likened to a revolution in the 1920s, just as Webb is revolutionizing our view of the world today. Let's consider how this realization came about, the evidence supporting it, and the contradictions. The first indication of the universe's expansion came from Vesto Melvin Slipher, an American astronomer who studied the spectral lines of galaxies in the 1910s, finding that many exhibited a redshift, indicating they were moving away from us. The decisive breakthrough came in 1929 when Edwin Hubble, another American astronomer, discovered the relationship between the distance of galaxies and their escape velocity. Hubble used the Doppler effect to measure this relationship. Edwin Hubble used the Doppler effect to measure the speeds of galaxies and found that more distant galaxies were moving away from us faster. This led to the formulation of Hubble's law, which states that the speed at which a galaxy moves away from us is proportional to its distance. For a long time, this law was regarded as the first clear proof that the universe is expanding. In addition to the redshifts, there is further evidence for the expansion of the universe. The cosmic microwave background, or CMB, is the background radiation of the universe dating back to when the universe was about 380,000 years old. It was discovered in 1965 by Arno Penzias and Robert Wilson. The uniform temperature distribution of this radiation in all directions indicates that the universe was once much denser and hotter and has been expanding ever since. Further evidence is provided by the Big Bang nucleosynthesis, which states that the abundance of light elements such as hydrogen and helium formed in the early universe is consistent with predictions of an expanding universe. Despite this evidence, there are also contradictions and unresolved questions about the idea of expansion. The most interesting of these is the Hubble tension. Hubble tension refers to a discrepancy between the values of the rate of expansion of the universe when different methods are applied. One method for determining the Hubble constant uses satellite observations of the CMB. The measurements were carried out with the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, among others. These measurements always result in a Hubble constant of about 67 to 68 km per second per megaparsec. Another method uses so-called standard candles, whose light provides fixed points for measuring distances and speeds in the universe. Scientists use Cepheids and Type 1a supernovae in particular as such standard candles. Cepheids are pulsating stars whose luminosity is related to their pulsation period. Type 1a supernovae have a standardized brightness, and by measuring their apparent brightness, distances can be determined and combined with redshifts to calculate the expansion rate. This method yields a higher Hubble constant of about 73 to 74 km per second per megaparsec. Several explanations for this discrepancy have been proposed in the past. There could be a systematic error in the measurement methods or assumptions, resulting in distorted results. Many researchers suspect a misunderstanding in the theories of dark matter and dark energy. Both are said to make up the vast majority of the universe, but we have not yet been able to measure or prove them, so we know very little about their true properties. Previously unknown aspects of dark matter and dark energy could explain the tensions. According to James Webb's current observations, scientists even suspect that dark matter and energy could change their properties, making them physically unmeasurable or undeterminable. If this is true, we are very unlikely to ever be able to scientifically describe the universe in its entirety. However, there are other explanations for the Hubble tension. The standard candles could be influenced by their respective surroundings and thus not be reliable measurements after all. At the moment, it looks as if we are heading towards a new physics that will bring new insights and models. The expansion, or rather the drifting apart of certain areas of the universe, is certainly not a lie but a clearly observed fact. However, it's currently unclear whether the entire universe is really expanding and whether it is drifting apart evenly. Observations of areas with a slower expansion and of phases with an increase in the rate of expansion rather suggest that we are in an overall dynamic structure. However, this does not necessarily have to have had a single starting point. Has Michio Kaku found the answer? Michio Kaku is one of the new scientists who see an opportunity in the current crisis. Kaku is known for his ability to make complex scientific concepts simple to understand, and he has long said that our old cosmology cannot be right. In Kaku's scientific work, the multiverse is the most likely scenario. In other words, he envisions a cosmos in which many universes exist, and in some of these universes, completely different physical forces can be at work. Kaku does not see the Big Bang as the definitive beginning of everything. If it really did exist, it was only the start of our universe, which is just one of many. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old. Its discovery in 1965 by Arno Penzias and Robert Wilson was a groundbreaking moment in cosmology. This radiation is remarkably uniform, suggesting that the universe was once in a hot, dense state and has been expanding ever since. This observation fits well with the Big Bang theory, which posits that the universe began as a singularity and has been expanding over billions of years. Big Bang nucleosynthesis, another pillar of evidence for the expanding universe, refers to the formation of light elements in the early universe. The observed abundances of hydrogen, helium, and other light elements match predictions made by the Big Bang model, reinforcing the idea of a universe that has been expanding and cooling over time. However, the Hubble tension poses a significant challenge to our understanding of cosmic expansion. The Hubble constant, a measure of the universe's expansion rate, varies depending on the method used to determine it. Measurements from the cosmic microwave background radiation, conducted by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, consistently yield a Hubble constant of about 67 to 68 km per second per megaparsec. In contrast, measurements using standard candles, such as Cepheid variables and Type 1a supernovae, suggest a higher value of about 73 to 74 km per second per megaparsec. This discrepancy has sparked considerable debate and research. Some scientists believe that systematic errors in the measurement methods could be responsible for the differing results. Others suspect that our understanding of dark matter and dark energy, which constitute the majority of the universe's mass-energy content, might be incomplete. These mysterious components could have properties that we have yet to fully understand, potentially accounting for the observed tensions in Hubble constant measurements. The James Webb Space Telescope has provided new data that may help resolve these issues. Its observations have led scientists to speculate that dark matter and dark energy might change their properties over time, making them difficult to measure accurately. If true, this could mean that our current models of the universe need significant revisions. Another potential explanation for the Hubble tension involves the reliability of standard candles. Cepheid variables and Type 1a supernovae, used to measure cosmic distances, could be influenced by their environments, leading to inaccurate measurements. This possibility suggests that our understanding of the universe's expansion may be more complex than previously thought. Despite these challenges, the concept of cosmic expansion remains a well-supported observation. The universe is undoubtedly expanding, but the exact nature of this expansion and its implications for cosmology are still subjects of active research. Some regions of the universe appear to be expanding more slowly than others, and there are periods when the rate of expansion seems to have increased. These observations suggest a dynamic universe that does not necessarily adhere to a simple, uniform expansion model. Michio Kaku, a prominent theoretical physicist, sees the current crisis in cosmology as an opportunity for new discoveries. Kaku has long argued that our traditional cosmological models may be incomplete. He advocates for the multiverse theory, which proposes that our universe is just one of many, each with its own set of physical laws. In this view, the Big Bang might not be the absolute beginning but rather the start of our particular universe within a larger multiverse. Kaku's ideas, once considered fringe, are gaining traction as new observations challenge established theories. The discoveries made by the James Webb Space Telescope and other instruments suggest that we may be on the verge of a new era in physics. This new physics could provide deeper insights into the nature of dark matter, dark energy, and the fundamental forces governing the universe. As we continue to explore the cosmos, the Hubble tension and other anomalies remind us that our understanding of the universe is still evolving. The expansion of the universe, a cornerstone of modern cosmology, is a complex phenomenon that may require new theories and models to fully explain. Michio Kaku and other forward-thinking scientists are leading the way, seeking to unlock the mysteries of the universe and redefine our place within it.